March 10th, 1892, Providence, Rhode Island. The machine shop floor trembled as riggers lowered a 70-ton flywheel onto its bearing journals, the polished rim spinning true, with intolerances measured in thousandths of an inch. Through clouds of coal smoke and the hiss of test steam, the latest Corliss engine took shape in George Corliss's works, a monument to cast iron engineering that critics had already condemned as obsolete before it cut its first revolution. No lightweight design, no simplification for ease of maintenance, no concessions to the newer high-speed engines flooding the market. Just 200,000 pounds of precisely machined iron built with valve gear so complex that factory owners questioned whether any mill engineer could keep it running. Engineering journals called it oversized. Efficiency experts labeled it too expensive. Competing manufacturers insisted their simpler engines would outlast this elaborate mechanical dinosaur. Yet in 2005, descendants of that mocked 1892 design still turn, in museums and heritage sites, their valve gear opening and closing with the same precision George Corliss engineered 130 years ago. While the high-speed engines that replaced them rusted into scrap decades ago, these massive machines stand ready to generate power, with nothing more than steam pressure and the mechanical genius cast into their frames. The most decisive engineering vindication in industrial history wasn't written in patent disputes or argued in technical journals, but proven through relentless service, cast into American iron using principles that made reliability inevitable. Thomas Mackenzie ran his hand along the engine's massive crosshead guide, feeling the oil film that had kept metal from touching metal for 43 years. The 1892 Corliss sat silent in the corner of Riverside Cotton Mill's powerhouse, its 70-ton flywheel motionless for the first time since Grover Cleveland's second term. Steam gauges read 0. The line shaft overhead hung still, no longer transmitting power to 3 floors of textile machinery. His assistant Robert examined a newer Macintosh Seymour engine across the powerhouse while Thomas opened the throttle valve by hand, listening to steam whisper through passages machined in autopsy. Smooth, even flow with no vibration telegraphing through the valve chest. The engine's main bearings had been poured with fresh Babbitt metal twice since installation, once in 1915, again in 1934. Still carried the original 30-inch diameter journals. Not bad for iron that had been converting steam pressure into rotational power when William McKinley was president. The Corliss's bed plate stretched 30 feet across the powerhouse floor, a single casting that weighed more than some complete modern engines. Ribbed for stiffness and aged for years before final machining, the frame had absorbed millions of power strokes without developing a single crack. No bolted assemblies to work loose, no welded joints to fail from fatigue. Just engineered cast iron with enough mass to turn vibration into heat and enough precision to maintain geometry across decades of continuous service. The valve gear rose from the cylinder heads in gleaming complexity, wrist plates, eccentric rods, dashpots, and trip mechanisms that controlled steam admission with a precision that still impressed modern engineers who bothered to study the ancient machinery. George Corliss hadn't invented the steam engine when he patented his valve gear in 1890, but he had solved the problem that made most stationary engines wasteful, inefficient machines. Standard slide valve engines admitted steam for the entire piston stroke, using expanding steam pressure inefficiently and consuming coal like blast furnaces. Corliss's system cut steam admission at precisely the right moment, allowing expansion to complete the stroke while using a fraction of the fuel. The complexity was undeniable. 4 separate valves per cylinder, 2 for steam admission, 2 for exhaust, each operated by its own mechanism. Eccentric rods drove wrist plates that oscillated trip arms connected to valve stems through dashpots filled with oil. The governor controlled cutoff timing through a linkage system that adjusted steam admission based on load. When the mill demanded more power, the governor opened valves longer. When load decreased, earlier cutoff conserved steam. James Morrison, chief engineer at the rival Buckeye Engine Works, had declared in an 1891 technical paper that the design would never survive industrial service. Too many moving parts, too many adjustment points, too much complexity for the average mill engineer to maintain. His company manufactured simple slide valve engines with 1/10 the mechanism and 1/3 the price. The Stevens Institute of Technology published comparative tests in 1893 showing that Corliss engines required 3 times the maintenance hours of simpler designs. Factory owners read the reports and hesitated, wondering if fuel savings would offset higher labor costs. Mechanical engineering students learned the Corliss system as a cautionary example of over-engineering, brilliant in theory but impractical for real-world service. Robert examined the valve gear through the engineer's practiced eye, noting how each component moved in mechanical harmony. Thomas pulled a grease-stained manual from the shelf, its pages thick with adjustment procedures and maintenance schedules. The philosophy was simple: maintain it according to specifications, and it maintained itself. Thomas demonstrated the governor system, manually rotating the flywheel to show how centrifugal force moved the weights outward against spring tension. As the weights rose, a linkage adjusted the trip mechanism that controlled valve timing. Load increases pulled the weights inward, lengthening steam admission. Load decreases allowed the weights to rise, shortening cutoff. All mechanical, all proportional, all self-regulating, without electronic controls or human intervention. The dashpots prevented shock loads on the valve stems. Corliss understood that rapid movements caused wear, so he designed progressive deceleration into every motion. The dashpot pistons moved through oil thick enough to slow valve closure gently, protecting seating surfaces from impact damage that destroyed simpler valve systems. The critics had focused on complexity, while missing the underlying philosophy. Every complicated mechanism served a purpose: reducing wear, improving efficiency, or enabling adjustment. The valve gear wasn't over-engineered, it was engineered for century-long service in an era when most engines were lucky to last 20 years. Each adjustment point had a specification. Every bearing had a maintenance schedule. Nothing was left to guesswork or chance in a system designed to outlast the men who built it. The Alice Reliance Works in Milwaukee received an order in January 1893 that would settle the Corliss debate through empirical testing rather than theoretical arguments. The Chicago World's Fair needed power, massive, reliable power to illuminate the White City and drive the machinery exhibitions that would showcase American industrial might to the world. Fair organizers demanded efficiency tests before awarding the contract. George Westinghouse entered his compound steam engines. The Ball Engine Company submitted their high-speed designs, and Alice Reliance, building Corliss engines under license, installed a 2,000-horsepower behemoth that critics said would consume coal faster than ships could deliver it to the fairgrounds. The testing protocol was brutal by 1893 standards. Each engine ran under measured load while engineers calculated coal consumption per horsepower hour. Water consumption, steam pressure, exhaust temperature, every variable that affected efficiency received precise measurement. The results would determine which engine powered the fair and, more importantly, which design would dominate American industry for the next generation. The Corliss engine consumed 13.4 pounds of coal per horsepower hour under full load. Westinghouse's compound engine required 16.2 pounds. The high-speed entries burned through 18 to 22 pounds for the same work output. The difference represented millions of dollars in fuel costs over a typical engine service life, and factory owners across America paid attention. Competing manufacturers declared the results impossible and demanded verification. Independent engineers from MIT and Cornell repeated the tests under controlled conditions. The results held. The Corliss valve gear, with all its complexity and adjustment requirements, extracted more work from each pound of coal than any competing design. The mechanism critics called impractical had just proven itself the most efficient power source in American industry. Thomas showed Robert the efficiency records Riverside Mill had kept since installing their Corliss in 1892. Coal consumption logs stretching back 43 years, each entry documenting pounds burned per hour of operation. The numbers told a remarkable story. 1892, 14 pounds per horsepower hour. 1910, 13.8. 1925, 13.5. The engine got more efficient as it broke in. The improvement came from bearing surfaces wearing into perfect conformity, valve seats lapping themselves tight, and piston rings bedding into cylinder walls with microscopic precision. Modern engines degraded with use. The Corliss improved its massive castings and generous bearing areas, allowing components to mate rather than wear out. Robert examined the steam chest, noting how the separate admission and exhaust valves eliminated the compromises inherent in slide valve designs. Efficiency bought forgiveness for complexity. A mill owner could hire a skilled engineer to maintain the valve, gear, and still save money on coal. Once understood, the system became predictable. Every adjustment point had a specification. Every bearing had a maintenance schedule. The 1893 tests had transformed the Corliss from an over-engineered curiosity into the standard against which all other stationary engines were measured. The machine that experts mocked before it ever turned into a revolution had just proven itself superior to every competing design through the one metric that mattered most in industrial service. Efficiency translated directly into profit. The metallurgy mattered more than the valve gear, though few engineers in 1892 understood why. George Corliss insisted on casting specifications that seemed wasteful to cost-conscious competitors. Thick sections where thin walls would suffice, massive frames where lighter structures might work, and aging periods that delayed delivery by months. The bedplate casting for a typical 500-horsepower Corliss weighed 40,000 pounds, poured from gray iron with carefully controlled carbon content. After casting, the raw iron sat in the foundry yard for 6 months, allowing internal stresses to relieve themselves through microscopic dimensional changes. Only after this natural stress relief did machinists cut the first chip, creating bearing surfaces and mounting pads that would hold geometry for decades. The flywheel represented the pinnacle of 19th-century casting technology. 70 tons of iron, spinning at 75 revolutions per minute, stored enough kinetic energy to smooth the pulses from each piston stroke into continuous rotational power. The rim measured 4 feet wide and 8 inches thick, balanced so precisely that the entire mass ran without vibration even after 40 years of service. One-piece casting, no segments bolted together, no weak points where fatigue cracks could develop. Thomas tapped the bedplate with his knuckle and listened to the solid thunk of dense metal. Mass absorbed shock loads. Thickness resisted fatigue. Corliss didn't skimp on iron because he understood that weight equaled reliability in reciprocating machinery. The cylinder bore measured 30 inches in diameter with a 48-inch stroke, dimensions that produced smooth power without the violent acceleration on forces that destroyed high-speed engines. Lower piston speeds meant reduced bearing loads, less friction, and longer component life. Where modern engines achieved power through speed, the Corliss generated it through displacement and pressure. Robert calculated the comparison on paper. A high-speed engine might complete 300 revolutions per minute, producing power through rapid piston movement. The Corliss turned 75 times per minute, using cylinder volume and steam pressure instead of mechanical violence. Fatigue damage accumulated with every stress cycle. Half the speed meant half the cycles meant double the service life, and the Corliss ran at 1/4 the speed of those modern engines. The connecting rod alone weighed 3,000 pounds, forged from crucible steel and machined to tolerances that seemed excessive in 1892. The rod's cross-sectional area far exceeded the stress calculations required for safety, but Corliss had learned that generous sizing prevented the flexing that caused bearing failures in lighter designs. The massive rod converted piston force into rotational motion without bending, twisting, or developing the fatigue cracks that plagued competitive engines. Even the small components reflected the same philosophy. Valve stems measured 2 inches in diameter, where competitors used 1-inch stock. Bearing journals ran 4 inches longer than calculations suggested. Bolt holes were reamed rather than drilled, creating precise fits that prevented fretting corrosion. Every design choice prioritized longevity over initial cost, creating a machine that cost more to build but less to own across its service life through decades of reliable operation. The proof arrived not in engineering journals but in mill ledgers documenting decades of continuous service. Riverside Cotton Mill's 1892 Corliss had powered 3 floors of textile machinery through 2 world wars, the Great Depression, and the rise of rural electrification. The engine ran 2 shifts daily from 8 to 1924, then 3 shifts through the war years when defense contracts demanded maximum production. Maintenance logs told the story in mechanical detail. 1895, repacked piston rod glands. 1898, replaced valve stem packing. 1903, rebabbited main bearings. 1907, replaced governor drive belt. 1912, reground valve seats. The work required skilled labor, but nothing approaching a major overhaul. The engine accumulated 40,000 hours of service before requiring its first significant component replacement, a piston ring set that had worn beyond specification after supporting steam pressure for 23 years. Thomas pointed to the newer engine installed in 1920 as Riverside expanded capacity. The Macintosh Seymour had seemed modern when installed, promising the same power output from half the weight and floor space. Engineers praised its compact design and simplified controls. 35 years later, it had been rebuilt twice. New pistons, new valves, new bearings, even replaced sections of the cylinder because it developed steam leaks that couldn't be repaired. The higher operating speeds created bearing loads that exceeded the metallurgy available in 1920. Journals overheated, bearings failed, piston rings broke from thermal stress. The engine spent more time under repair than the ancient Corliss it was supposed to replace. Robert examined maintenance records from other installations, finding similar patterns across American industry. A 1889 Corliss at the Pullman Palace Car Works in Illinois ran until 1962, 73 years of daily service with 4 major maintenance overhauls. The Pratt & Whitney complex in Hartford, Connecticut operated a pair of 1,500 horsepower Corliss engines from 1886 to 1948, powering the machine shops that built precision measurement tools and aircraft engines. When the factory finally converted to electric power, both engines were still operational, retired not from failure but from obsolescence. The most remarkable example came from the Nordberg Manufacturing Company in Milwaukee, which installed a 2,500 horsepower Corliss in 1890 to power its own machine shops. The engine ran until 1909, 89 years of service that spanned horse-drawn delivery wagons to moon landings. Engineers who maintained the machine in its final decades reported that the valve gear still operated within original specifications, the flywheel remained balanced to modern standards, and the main bearings showed wear patterns measured in thousandths rather than the hundredths that would require replacement. Thomas let the number sink in. 90 years. That Nordberg engine outlasted every replacement technology invented during its service life. Electric motors, diesel generators, gas turbines. None of them offered enough advantage to justify scrapping a machine that still worked perfectly. The mills that trusted Corliss engineering had gained competitive advantage measured in decades of reliable power, while factories that chased newer technologies faced constant replacement cycles that consumed capital without improving productivity. The engineering principles that critics dismissed as overcomplication in Sinu had proven themselves fundamental requirements for longevity by 1935. Every feature that seemed excessive, the massive castings, the complex valve gear, the generous bearing areas, served specific purposes that became obvious only after decades of service. The separate admission and exhaust valves eliminated the compromise inherent in the slide valve designs where a single valve controlled both functions. Corliss valves opened quickly and closed positively, creating sharp cutoff that maximized expansion efficiency while minimizing the rubbing friction that wore slide valves into leaking failures. The dashpots that cushioned valve closure absorbed impact forces that would have hammered the seats into premature wear. Thomas showed Robert the main bearing journals that had supported the flywheel for 43 years, 30 inches in diameter with 24 inches of contact length. That meant 1,800 square inches of bearing surface. The Macintosh Seymour had maybe 400 square inches supporting similar loads. The math was simple. Bearing pressure equaled load divided by area. Lower pressure meant less friction, less heat generation, and exponentially longer bearing life. The Corliss's generous sizing kept bearing pressures below 60 pounds per square inch, even under peak loads, pressures low enough that oil films could separate metal surfaces completely, preventing the contact wear that destroyed smaller bearings. The governor system demonstrated similar engineering wisdom. Critics had focused on the mechanism's complexity while missing its fundamental superiority to simpler throttle-controlled engines. Throttle governing restricted steam flow before admission, creating pressure drops that wasted energy. The Corliss governor adjusted cutoff timing instead, allowing full steam pressure into the cylinder but controlling how long admission valves stayed open. The difference was subtle but significant, 5 to 8% better efficiency across all load conditions. Robert examined the trip mechanism that controlled valve timing, noting how adjustment screws allowed precise calibration of cutoff points. Cotton mills ran steady loads, same power demand hour after hour. Engineers would set a cutoff for maximum efficiency at normal load and leave it, but machine shops with variable loads needed constant adjustment, and the Corliss governor handled it automatically. No human operator could respond as quickly or precisely. The thermal design proved equally thoughtful. The steam chest and cylinder jacketing maintained metal temperatures that prevented condensation losses while avoiding the thermal stress that cracked cylinders and engines that ran too hot. Corliss had calculated the balance between efficiency and durability, choosing temperatures that sacrificed a few percentage points of theoretical performance for decades of reliable service. Even the installation details reflected long-term thinking. The bed plate sat on a concrete foundation thick enough to absorb vibration and massive enough to prevent settling. Anchor bolts measured 2 inches in diameter where competitors used 1-inch stock. The engine room itself was built with the machine in mind: high ceilings for the tall frame, overhead crane coverage for maintenance access, and ventilation systems that kept bearing temperatures within specification through decades of continuous operation. The Riverside Mills Corliss made its final revolution on September 15, 1935, not from mechanical failure, but from economic reality. Rural electrification had reached Providence, and the utility company offered power at rates the coal-fired engine couldn't match. Thomas opened the steam valve for the last time, watching 43 years of service end not in catastrophic failure, but in quiet obsolescence. The engine stood complete and operational, every system functioning within specification, ready to run another 40 years if circumstances required. The flywheel's rim still ran true. The valve gear still timed admission precisely. The bearings still carried loads without excessive heating. Only the economics had changed. Coal prices rising while electricity costs fell, creating a crossover point where even Corliss's legendary efficiency couldn't compete with centralized power generation. Robert watched steam pressure bleed from the system for the final time. The future belonged to electrical switches and power by the kilowatt hour, not to 70-ton engines that required skilled engineers to maintain. Some Corliss engines would find homes in museums. Most would meet the scrapyard, their iron melted down to build the machines of a new industrial age. But the legacy extended far beyond the individual machines. The Corliss valve gear had established principles that influenced every reciprocating engine that followed: separate admission and exhaust valving, automatic governor control, cutoff timing based on load rather than throttle restriction. Diesel engines, aircraft engines, even modern internal combustion engines incorporated features that George Corliss had pioneered in steam decades earlier. The manufacturing philosophy proved equally influential. The emphasis on generous sizing, quality castings, and maintainable design shaped American industrial equipment through the first half of the 20th century. Machine tool builders adopted similar approaches, creating lathes and milling machines that remained productive for generations. Electric motor manufacturers designed products for decades of service rather than planned obsolescence. The expectation that industrial equipment should last became embedded in American engineering culture. The irony wasn't lost on historians examining the Corliss era from the perspective of modern manufacturing. The engine that experts had mocked as over-engineered and impractically complex had outlasted every simplified design intended to replace it. The mechanism critics said would fail from excessive maintenance requirements had proven easier to service than supposedly simpler alternatives. The machine dismissed as a dinosaur had run longer than any of the evolutionary improvements that followed. Thomas looked at the silent Corliss one final time. 90 years in some installations. Corliss built these engines when America still believed machines should last, when engineers designed for service life instead of replacement cycles, when quality meant something more than initial cost. The proof of concept results spoke with historical certainty. The 1892 engine that experts mocked had run for a century in some installations, outlasting not just competing designs, but entire generations of replacement technologies. Steam power gave way to electric motors, which gave way to variable frequency drives and smart controls. But the fundamental lesson remained unchanged. that reliability came from engineering principles, not from technological fashion, and that machines built to last actually did.